Okay, so today is the last of this lecture series, and I remind myself what I'm supposed to do, which is to do Gauss quadratic again, but okay, and then how all this generalizes to higher dimensions, and we can, once we see the structure, the generalization is painless. Of course, it was not so easy for Riemann, who invented this. But Riemann was a smart guy and invented this whole subject. And of course, I never met Riemann, so I don't know how he was thinking. But we can try to reconstruct the thought process in any case. Okay, and then this is the Riemann curvature, and the last thing is gas dynamics. So might that be enough for 2 lectures, but we'll see how it goes. Okay, so last time I wrote down, first of all, I made a mistake in this formula for second fundamental form. Right, I had the Hessian dotted with the normal. That part was easy, and I was writing G inverse, but it's actually the inverse of the matrix G, not the inverse of the determinant. This is actually the inverse of the matrix G. So that's why I like to have G to be the identity at the point of evaluation, and I never make this silly mistake. Okay, so now let's go back. So this was the take a second derivative. You have a point on the surface. This was in 3 dimensions. So I have a point on the surface, and we're on U1, U2, U3. Of course, the standard one would be x is U1, U2, and a function of U1, U2. But this is the general formulation, so it doesn't make any difference. And we take a point on the surface, and then we differentiate twice. So this is a vector valued guy, and we decompose the vector into points in the tangent plane, which is the partial of x with respect to u1, partial of x with respect to u2. So this is in the tangent plane. And then this piece in the normal direction. So the geometry is very easy. So it's just orthogonal decomposition. So the projection onto the tangent plane, we use these capital gammas. And the projection onto the tangent direction is just these scalar guys, L, M, and N. Of course, it was easy to see what L, M, and N are. Just take the dot the normal in each case, and we see, of course, as I said, L, M, M, N is just the second, how did I write it there? Hessian dotted with the normal. Just dot to both sides. Okay, but we knew this is equal to G pi. Okay, by definition. Now, so far so good. And what else? What about these gammas? Well, it's the formula for the gammas, and it's rather lengthy, and it's a general shorthand formula. Okay, but the main thing to realize is the gammas only depend on E, F, and G, and E, F, and G in the surface case is just the classical shorthand for the metric. So this only depends on the metric. So it says the gammas just depend on first derivatives of the metric, and hence a known stuff if you know the metric. Okay, so now we wrote this in a shorthand form. So what's the shorthand? The shorthand was, I see that I did this last time, but let's look by a little inspection. You see the left-hand side is a second derivative, so it's an I or a J, either two I's or two J's. Okay, and then this guy is always the same as the derivative, so it's just gamma ij. Then it's multiplying the partial of x, and now it's 1, 2, 1, 2, so those agree. So now repeated subscripts mean sum, so that's the sum. And now we have, that's very nice, what's left over is this LMN. Okay, so I'll use the letter capital H, so it's some capital H, a 2 by 2, times, where capital H is precisely this guy. So I know how to find each of these guys very quick shorthand. So you don't have to write down the full story. But if I move the left hand, this guy to the left-hand side and put an equal sign, okay, we see that this is just an operator on first derivatives. Okay? It's a first derivative of a first derivative minus a first derivative. Okay? So let's give a name to this thing. So this thing we can do is, let's do it, so it's the partial, let's write it this way. So it's the partial of x with respect to uj. Let's do uj first, it doesn't make any. Okay. And then this is the partial with respect to uj, okay, minus so it says, I know how to operate on first derivatives. It says, if I have a whole list of first derivatives for each component of x, because this is component-wise, we match. So we freeze the component, say the first component. So I didn't put up a 1 here, or a 1 here, or a... Okay, to remind you, we do it component-wise. So it would be the first component of x, first component of x, first component of the normal. So we do it component-wise. So for each component, okay, then I take its first derivative. Okay, and it says to differentiate, you differentiate that one, that component of the derivative, and then subtract off, okay, linear combinations of all the first derivatives. So even though there's only one guy here, you need to know the whole family here, because they're all involved. Even though, okay, so here we'll say the first component differentiated with respect to x1, this one depends on the first component differentiated with respect to x1, x2, x3. So far so good? Okay, so we give a notation to that. So unfortunately, or fortunately, right, it tells us how to differentiate, okay, first derivatives. Okay, now in the language of the fancy, they talk about one forms, two forms, so, but in calculus language, it tells us how to differentiate first derivatives. So if I have a scalar valued guy, because that's just one component, I differentiate it, okay, with respect to x1, x2, x3, so I can say take its gradient. Now I have a vector, and this tells me how to differentiate vectors. Okay, it says if you want to differentiate a vector, okay, you differentiate the vector normal derivative, and then you subtract off these guys. And it's done, the formula says it's done component-wise. Okay, so this is a definition. So I write 3 bars, so that's just the definition. First of all, it makes the notation very simple. It says that this is, which was the Weingarten equations. Okay, which is this whole list, now become just okay, and this thing is called the covariant derivative. Okay, now I didn't need to think about x. As I said, it could have been any scalar. Even though here x is effective, but we do it component-wise. So any scalar tells me how to operate on scalars. So it says the covariant derivative of a vector is given by this formula. So I know how to differentiate covariant derivatives of vectors. Covariant derivative of a scalar is just normal differentiation. Nothing to worry about. Covariant derivative of a tensor, then you have more gammas. The covariant derivative starts getting, the formulas get lengthier and lengthier. But all we need is the covariant derivative of the tensor. Okay, so that's that. Okay, so now what is the Gauss-Codazzi equation? So I wrote down the, well, I said it's, we equate cross partials. Okay. Well, if we equate cross partials, okay, what are we going to do? We're going to take partial derivatives here, then subtract off partial derivatives there, and set them equal to each other. Okay, what will we get? Well, we'll get these guys, okay, when we have the equations, which will be, okay, so let's just think about that. When I take partial derivatives here, I'm going to get the partial derivatives of the L. So when I take partial derivatives here, I'm going to get partial derivatives of the H's. And when I do the subtraction, you get equality. Well, it's not surprising. First of all, it's easy to do. But it's very nice. So if I take the partial derivative of Hij, it should be equal to the partial derivative of, it doesn't make any difference. Hij is symmetric, so the partial derivative of Kj. So the Gauss-Codazzi equations are very simple. It says, take the covariant derivative of Hij and subtract off the covariant derivative of Hkj, and that's the Codazzi equations. So what's it look like? Well, okay. Well, now it's the partial derivatives of tensor, but okay. So the partial, this will tell me how to differentiate a tensor valued guy, and I can see, I'll be able to get the rules, in fact, for differentiating the tensor valued guy just by formally doing the derivatives here. So either way we can write it down. So let's write it down. The brute force. And then we'll have it and I won't throw it away. So the integrability condition, which is the Codazzi, so it's called Codazzi, except sometimes it's called Codazzi Mainardi, and sometimes it's called Codazzi Mainardi Peterson. So why all the names? Well, it was 1870, as they usually say. plus or minus epsilon, 1860s, People didn't have email. It's hard to believe at one time people didn't have email. At best they had telegraph and letters, right? So people could work, it was an important subject, so people worked independently and didn't necessarily communicate. So people derived these equations independently. So let me write down Can you read that? Gamma 1, 2, 1. Okay, so these are the Gauss equations. So if I want to, if I have a surface, then a necessary condition is that these cross partials be equal, which is the integrability condition. So the Gauss equations have to be satisfied. So that's one thing. And remember, we also had the Gauss equations. Okay? And the Gauss equations were just in the, it was the determinant of L, which is L n minus m squared equals the determinant of the metric EG minus f squared times the Gauss curvature. So if you give me the metric, so this is known if you give me the metric, if G is given. So if you tell me how to find distances on the surface, then I know, of course, the formula for the distances, but I know the Gauss curvature by Gauss's theorem egregium can be found from the metric by just differentiation and multiplication. So it says, okay, Ln minus m squared has to satisfy, the determinant has to satisfy the equality. So what does it say? From the point of view of PDEs, this is two PDEs and one algebraic equation. So one algebraic, ALG, which is three equations and three unknowns. So things match up. And on top of it, unlike the previous situations when I mentioned this embedding problem of finding the surface given the metric, it's not fully nonlinear. In this case, it's quasi-linear. So it's quasi-linear and hence much more amenable to our classical concepts of, here's the equation, elliptic, hyperbolic, parabolic. We know how to handle those cases. So depending on K, and I'll hopefully get to that, equation will be either elliptic, hyperbolic, or degenerate parabolic. Okay, so I did that. Now, next thing was higher order surfaces. So let's continue here. I don't want to erase anything. So higher order surface. So we, as I said, let's think how maybe Riemann was thinking. I'm not sure. So Riemann was thinking, before we had a surface that looked like x, u1, u2, and some function of u1 and u2. Right? That's how we be the typical representation. So here, I erased it. I'm going to erase this again, but anyway. So here's U1, U2, and the surface light above someplace. So this was, that would have been U3 equals a function of U1 and U2. So standard formulation of a surface. So what would it be a general? So let's think about it. It would be U1, U2, U3, UM. You just think of the generalization. And then F of M plus 1, which depends on all these guys. I don't want to write it out. So F depends on the previous list. F of M2 and F of N. So you see the natural generalization. That's why it's handier just to work with the X and not worry about the F's. Okay? So this would be lying on Rm. So the surface would be Rm dimensional surface lying in n-dimensional space. Now if n is m plus 1, then it's a hypersurface, because it's just one more dimension, as we have here. This is 2, and one more is 3. So if this was 3, okay, one more would be 4, and we consider hypersurfaces in three-dimensional space, etc. Okay? But in general, it can be here. Now, the notation makes sense, but can it always be done? And then you can give me a metric. Right? So the metric would depend on these guys. UM. And then we would ask the question, can you find a higher dimensional surface? And this is what Nash's existence theorem was. Locally, it's comparatively easy. Not that easy, but easy. Okay. But globally, to be able to do it, that give me a G globally defined, is there always an N such that you can get a complete surface? And that was Nash's theorem. So, for example, Nash's theorem says in the case of m equals 3, you can do it globally. I think the answer is n equals 12. And we don't know if that's the best number. Maybe it's 11. Okay, but that's what Nash says. And it can be done smoothly, C infinity. Okay, so now we see the concept. So the definitions go right through, except for some small point here. If I have a one-dimensional surface, a two-dimensional surface, it's clear what I mean by a normal. I take two tangents, take the cross product, I can take a computer normal. But three-dimensional surface, not so simple. So you have to know that there's a field of normals. Okay? So it's not just one normal vector. There's a normal vector for each. So the tangent vectors, let's write the tangents, we know what. So what are the tangents in general? So I don't want to erase. So the tangents are clear. So the tangents up through UM. So this are the tangents. Okay. I know how to find the tangents to the surface, whether it exists or not. Let's assume it exists, and then we'll find the necessary conditions. So this is the tangents. So how many tangents are there? There are m tangents. So this is the, this makes sense, so this is the projection onto those m tangents, the Weingarten equations. But now I have to have the rest. Well, what's missing? Well, it's clear. If those guys give me m tangents, then it better be n minus m plus 1 normals. And now I can do the decomposition. Before there was, oh, now I'm using, if the n isn't underlined, it's just the number n. Okay, so n minus n plus 1 normals. So in the case before, of course, it was 3 minus 2. But in general, okay, there'll be a lot of these, so this will be indexed by mu. So this will be mu equals m sub 1, mu equals m sub 2, and mu equals n. So there'll be a normal family of normals, n mu. I'll use lowercase or big. Oh, let's use lower. Okay. N mu will be a family of normals. Question? Did I make a mistake? N minus m. N minus m, sorry. Very good. Not a major mistake. The world won't come to an end, but yeah. N minus m. N minus m. Okay. So there's how many? So n minus m normal. So mu runs is there from m plus 1 all the way up to n. So the ideas are, again, I think this must have been how Riemann was thinking. He knew the 2D case. How should it go in 3D? So that means we have to change the formula slightly. Oh, so let's put the mu goes downstairs, sorry, because it's component-wise. So this says first component of the derivative of the first component of x equals this stuff operating on the first component of x equals this stuff operating on the first component of mu. So it's done component-wise. Okay, so now we see with no work and a little imagination, we've generalized the Weingarten equations. So now we know the Weingarten equations for arbitrary setup. Okay. Now, what else do we need to know? We need to know the generalizations of both the Gauss equations and the Cauchy equations. Well, it's not a big deal, it's just bookkeeping, right? You have to equate cross partials. When we equate cross partials, what are we going to get? We're going to get stuff that looks like this, okay? But because we have to differentiate now the whole family of n's, we get a whole bunch of other equations come from differentiating the n's. So we also have to have an equivalent system, not only decomposing, when we do the decomposition, we have to account for the partial derivatives of n. When we differentiate n, okay, that's also going to be decomposed into the tangent directions and the normal directions. So it has its own family of decompositions. So when we differentiate, let's not, okay, so now it's the generalization of Cauchy. Okay, we have to equate cross partials. Again, no big deal. We're going to have to differentiate the gammas and the n's, okay? And what do we get? When we equate cross partials, we get, again, a system, new system of Cauchys. Okay. But we also have to differentiate the n's, which is going to cause some bunch of new equations. And those are named after the Italian mathematician, Ricci. So you get more equations. It gets a little lengthy, but the idea, and that's all we try to get across here, is that there's nothing more than an integrability condition, which is gained by equating cross partials, and we get Codazzi and Ricci. Okay. Not so bad. So that's the first thing that has to be generalized, but we have to generalize the Gauss curvature. So how do we do that? So let's erase here and see how that's done. And I can only guess how Riemann was thinking. Oh, I shouldn't have, I erased it, so let's write it again. So I had pi was g inverse second derivative of x with respect to, well, it's the Hessian, okay, dotted with n. Okay, but let's just concentrate on pi for a second. Okay. So I know the determinant of pi will give me the Gauss curvature. Okay. Notice for each n, okay, if it's higher dimensions, that means for each n you'll get a pi, which makes sense because here it is. The pi and the h up to the multiple of the g, same idea. So far, so good? Okay, so we know for each pi we can get a g. For each mu we can get a pi. But let's think about how do we get the Gauss curvature. So let's look at a typical pi. So let's do it back to the previous example. So let's do the 2D case first. It's elementary linear algebra. What's one way, if given the matrix, how can I find the 1,1 component? I think, right, this is, if I multiply, you do it once, okay? Of course everybody knows this from linear algebra, but let's multiply. So I multiply this guy on this one, I get 1, 1. Again, if I didn't make a mistake. And then 1, 2. And then I multiply from the left by 1, 0. Okay, and I get 1, 1. Okay, etc. So if I want to know pi for any matrix, all I have to do is take a basis vectors, orthogonal basis, and I can see that this is pi hitting from, doesn't make any, from the left by the basis is, I'll write it in this form, so it would be E1, E1. That means hitting it from the left by vector E1 and from the right by vector E1. The notation is okay? It's the notation Morgan uses, so. So you take the matrix, you hit it from the so one way to represent the matrix is how it acts on the basis vectors. Okay, that's okay. So that is a linear. Given a linear operator, it has many representations as a matrix. Okay, not the same thing. But once you give me the basis vectors, then the linear operator can be represented as a matrix once you tell me the basis vectors. So far, so good? Okay. Okay, so let's say I'm given a surface, okay, higher dimensional surface. It lies above a plane, okay, so higher dimensional surface. It's going to have a tangent plane. Okay, we know what it is. Here's the tangent plane anyways. We just did it. It's the span of all that was m, right? So this was the tangents. So far, so good? Okay. So if I take two tangents, and I can do Gram-Schmidt, can make them orthogonal. Okay, so I can set up an orthogonal basis for the tangent plane. Okay, that means I have a way to do tangents two at a time. Just two at a time. So that means I'm taking really just sections. I can't do the whole tangent plane at once, but I can do sections. I can do two tangents, two tangents, two tangents, etc. Okay, so I can do tangents two at a time. So I can take, for example, 1, 0, okay, and then two tangents. So this one would be 1, 0, 0. Okay. Right? Two tangents. And this will give me, when I do that computation on pi, of course, will give me pi 1, 1. So I do two tangents, so I got that one with itself, then of course that's also, that'll give me pi 2, 2, etc. So that'll generate pi 1, 1, pi 2, 2, pi 1, 2, pi 1, 2. Very good. So now I'm in the case of 2 by 2. I've considered just a two-dimensional tangent plane, just doing with these two, which was these two, E1, E2. Okay. And now I'm just in the two-dimensional case. If I'm in the two-dimensional case, I know how to take Gauss curvature. It's very simple. How do I take Gauss curvature? I take the determinant. So I know how to take the determinant in groups of 2 by 2. I don't take the full determinant. That doesn't make any sense because Gauss curvature was only a two-dimensional guy. So I only do it 2 dimensions at a time. Make sense? Like the first one. This one, okay, I've computed this guy, and that one, now I take the determinant, and now to that 2 by 2 determinant I have a Gauss. It's the Gauss curvature. Right? Well, now you got the idea. Okay. It's not the determinant of the full pi. So you give me the full pi. Okay. Don't take its determinant. Okay. 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 Let's just do. So it's one of the mu's. Doesn't make any difference. 1, 1, 1, 2, 2, 2. Which one? 2, 3? Sorry to bore you. This would be 3, 1, but it's symmetric. Yeah. So as I say, I guess this was what Riemann was thinking. As I said, how do we exist in this world? How do we go through life? We reduce to the previously solved problem. So Riemann was building on his thesis advisor's work. Always build on your thesis advisor's work. Take advantage. So not everybody has their thesis advisor being Gauss, and not every student is Riemann. But nevertheless, the idea process makes sense. He knew what Gauss had done. He thinks, oh, I know how to do the case above a 2 plane, so I just keep doing 2 planes. And I consider all the 2 planes. Well, what's it mean to do all the 2 planes? As I said, the first one was 1, 0, 1, 0, it was the E1, E2. But then there are other two planes. So you get this determinant, and I'll use the color, or that determinant, or did I leave? That determinant. Okay, there were 6. Okay, so what is it giving? It's the, so we need the 2 by 2. It's 2 by, we reduce everything to 2 by 2 determinants. So need to do 2 by 2 matrices. So we take 2 by 2 determinants, and then we're getting 2 by 2 determinants. If we take all these 2 by 2 determinants, okay, we get a big guy. Okay, so in this case it could be substantial. So we can take 2 by 2 determinants, okay, and we get a big guy, and we can write it down, but it's the Riemann curvature tensor. So just as before, the standard 2 by 2 determinant gave us the Gauss curvature. Okay, when we do all these two by 2 determinants of the higher order guy, could be 3 by 3 or n by n. Okay, so it's getting, but this will determine the Riemann curvature tensor. So the generalization of the Gauss curvature is the Riemann curvature tensor, which is nothing more than doing Gauss curvature 2 by 2 pairs. So the only thing that enters, the only nonlinearity from the point of view that it enters the problem, even though it's even higher dimensions, it's never worse than a 2 by 2 determinant. So that gives us the Riemann curvature tensor. So that is one statement, but then that was the generalization of the Gauss curvature, so no determinants, but 2 by 2. But how about Gauss's theorem of Regium? Okay. Remember, we need the Gauss equations if we're going to solve anything. So that also has to be generalized. So before, it said that the Gauss curvature was only a function of the metric, so second derivatives. So now it should say that the Riemann curvature tensor is also a function only of the metric. Okay, so we need a generalization of Gauss's theorem of Regium. But fortunately, we have that. And now we're finished. So it says, now let me write RIJKL by definition, and we're RIQJQJKL. Okay. So the Riemann curvature tensor, you can write it either all lower subscripted or an upper subscripted. Okay, and sorry. This one is RJKL, sorry. It's RJKL and I. So there's 2 ways to do it. Just a definition. Okay. So you can write it 1 upstairs and 3 downstairs, or 4 downstairs, and the relationship between the 1 upstairs and the 3 downstairs says this is the inverse of G. Multiply by the inverse of G. This Q hits this Q and produces the I. So this is G inverse. Of course, at a place where the G is the identity, then it's the same thing. Not important. The important thing is we need the generalization of Gauss's theorem of Regium. And it says RIJKL equals, and now I have to remember exactly what it is. It's K, it's ijk, no, it's ii upstairs, and gamma, and then K and L. And now what's missing? So we had the i's, so it's the J and this should be J. So here's the K, here's the K, here's the L, so it should be JL, let's see. So this is JL, so this should be LJK. Okay, so now everybody depends on IJKL. Okay. So it's the lack that the interchanging L and K here, okay, it doesn't commute. Okay, so it doesn't commute, and the difference in the commutativity is the Riemann curvature tensor. But remember, even the formula I wrote upstairs in this surface case, gammas depend on first derivatives of G. And this is derivatives of the first derivative. So this says, okay, the Riemann curvature tensor depends on second derivatives of G, just as in Gauss's theorem of region. So Riemann did two major things here. Okay? He generalized the notion of Gauss curvature by doing sections, and then he found, okay, the generalization of Gauss's theorem of Regium, which was the non-commutativity of the covariant derivatives on the gammas. So now we've put everything together, everything generalizes, and okay, so I've done by sections meant by 2 by 2 pieces. I did the Riemann curvature tensor. So now I have 10 minutes to do gas dynamics, which is a whole story in itself, but let's quickly do it. And I'll give you the idea. So let's erase everything. So if I can remember the equations, it was L, M, and N. So now just back to the surface case. Surface, a 2D surface in R3. Okay, so then we had L, M, and N, and we had the partial derivatives. So let's see. So it's a partial, I don't know what the left-hand side is. The partial of L with respect to U2 is minus the partial of M with respect to U1 equals some stuff on the right-hand side. And then it was the partial of M with respect to U2, going that way, minus the partial of N with respect to U1 equals some stuff on the other side. Okay, so let's rewrite this just trivially. I'm moving this one over here. And the partial of the other one is M with respect to U1 minus the partial of L with respect to U2. And I move that one over there. Okay, so the same thing. And now I'll erase here. So we had to satisfy those equations, and so this is the Kodazzi. And then we had to satisfy the determinants, which is Ln minus m squared equals known stuff. K e.g. minus f squared. So if we want to find the surface given the metric, the embedding problem, we have to solve the quasi-linear system. Okay, now this quasi-linear system should come familiar if anybody ever studied gas dynamics. So what are the equations of gas dynamics? Euler equations. So gas dynamics steady, compressible, irrotational. Okay, so if the gas is moving, not accelerating, the gas can be moving, but not accelerating, that means steady. Okay, compressible means I can squeeze it. Okay, irrotational means there are no vortices being set up, no spinning. So if I write rho is the density of the gas, u is the velocity, uv pair is the velocity of the gas. Okay, and then I need the pressure in the gas. Okay, which is, for a compressible gas, the standard one is rho to the gamma over gamma, where gamma is a number greater than or equal to 1. Okay, you can put another constant in there, but needless to say, I put the gamma in like other mathematicians. Doesn't make any, because when you differentiate it, you get rho to the gamma minus 1. Okay, so what are the equations of gas dynamics? Well, it's conservation of mass, okay, momentum. Okay, so let's write down and the rotationality. Okay, since time is running short, let's do momentum right away. So what's conservation of momentum? Conservation of momentum, if there was acceleration, but there isn't, okay, would be the rho squared plus p d dy, if I use x and y as the two variables, u squared plus rho uv, okay, equals 0. If there are no forcing terms. And this one would be d dx rho uv plus d dy rho v squared plus p equals 0. Now if there was acceleration, we have d dt rho u and d dt rho v. But I said no acceleration, steady, steady. Okay. So if you look at it, don't these look the same? So d dx, if u1 is x, here's n, here's n, right? Here's n. Here's m, actually minus m. Here's m. And I ran out of colors, so I'll have to use white, okay. And there's L. So I should write this with a minus, because it's with m, so I should write this minus plus. So multiply both sides, I switch the sign on the right-hand side. So the Cauchy equations look exactly like the steady-state gas dynamic equations. Okay. What does ln minus m squared become? Well, if you plug it in, okay, that has to be satisfied. That means when you plug it in, there has to be a relationship between rho, u, and p. Okay. So there's 1 and v, that's 4. But if I tell you what p is, that means it's 3. So this one becomes as a relationship between ln and m and p in gas dynamics if p is rho to the gamma. So p is rho to the gamma. So this is rho to the gamma. So there are 3 variables here, u, rho, and v. So in gas dynamics, it means there has to be a relationship between rho, u, and v if they're to look the same. But of course there is in gas dynamics. That's the Bernoulli relation, which if I had more time, I would derive. But the Bernoulli relationship in gas dynamics is rho equals 1 minus, I think, I have to remember exactly, q to the 1 over gamma minus 1, and q, I think something over here with a q squared. And Q is U squared plus V squared. So the main point, in gas dynamics, rho is related to U and V. And in here, rho is related to U and V. Okay. Okay. Now that only works, you can derive Bernoulli in the irrotational case. How do you derive Bernoulli? Okay. It comes from the conservation of mass and the two unknown unused equations. So these two, oh, my phone? You can say hello. Okay. And so conservation of mass and irrotationality give Bernoulli, so that one. How do we get this one? Well, not very deep. Then I'll stop. Take the determinant, because we know the identification. So rho u squared plus p, rho v squared plus p multiply minus rho u squared v squared equals known stuff. So when you plug that in, that gives the geometric Bernoulli. So what's the point? Okay. It means the problem of surface theory is mapped one-to-one onto the problem of gas dynamics. The only thing that makes them different and why the geometry is even harder than this problem, which is quite hard, is because you have a right-hand side, the L, M, and N. So it's a non-homogeneous quasi-linear equation. But the ideas that we use over here and the concepts we use over here, we use over here. What makes gas dynamics hard is the plane is going through the air, steady state, and what can happen? Well, the plane going through the air, okay, we can have, the plane can be going slow, in which case it's subsonic, lower than the speed of sound. Or the plane can be going very fast, in which case it's supersonic, faster than the speed of sound. Same thing in geometry. We can have subsonic geometry and supersonic geometry. So when people ask me what I work on, I say I work on transonic geometry, where they can switch from supersonic to subsonic in one place. So in gas dynamics, m is the Mach number. Okay, isn't it? Okay, and this is subsonic. And I'll stop in a minute. And this is supersonic. One-to-one. What's the translate into here? Gauss curvature positive, Gauss curvature negative. So Gauss curvature negative is supersonic, Gauss curvature positive is subsonic. But supersonic is hyperbolic equations, subsonic is elliptic equations. K equals 0 when m equals 1, transonic, you're going through the sound barrier. So we see a complete analogy. Then I always ask, okay, now I understand 2 dimensions. How about Riemann's theory in higher dimensions? What does it mean mechanically? But that would take another story. Anyway, it's a good place to stop. Thanks for your attention.